Hi everyone, this is part one of the applications for exponential and log functions. We're going to take a look at some compound interest today, and then we're going to look at a couple other common areas of applications using logs, half-lives being a major one, and just some growth and decay type questions. So to begin with, we'll take a look at compound interest, which is something that you probably did a little bit of in pre-calc 11. It's one of the most important real-life concepts of things that you would take away and say, like, okay, here's a way in which I can really profit from knowing about how compound interest functions, or here's a way that compound interest can really affect me if you're talking about some form of a debt or loan or something like that. To refresh ourselves, we have our formula for compound interest right here, and this should be something that maybe you've seen in the past before, but we'll try to build it up a little bit. But because we learned it in finance for pre-calc 11, I won't go into the exact same detail. So just to recap, P is going to stand for your principal. That's the amount that you start with. So if you start with a lump sum of $1,000, then you would say that's what your principal is. So in brackets here, this is what you start with. R is going to be the interest rate. And just understand that it's expressed as a decimal. So for instance, 6% would be written as 0.06. N is going to represent our number of compounding periods. And so what that means is you're going to get some questions here where they'll say, if you compound interest annually, that's once per year, your N value would be 1. But if you compound something semi-annually, then that would be saying that you have something happening twice a year. So your N would be twice. Think of the semi-annual sale that you see in stores sometimes or something like that. If you compound monthly, it would equal 12. If you compound weekly, it would be 52, and so on. And then T is going to represent the time in years. So A is our answer, but I like to call it your accumulated amount. Oops. It's the amount that you have at the end of all of this. And so that's our compound interest formula. It should look a little bit familiar, but let's see what we could do with some questions and figure out how this works out. Okay, example number 1. Find the interest if $6,500 is deposited into an account paying 6% compounded monthly for 5 years. So this question, I'd say to get started with, I would recommend always writing out your formula until you have it down. And then over here, I would write what we're going to be able to fill in, and then we'll see what we need. So what you could say is if you want to find the interest on $6,500, your principal is $6,500, and that was done at 6%. Your rate is 0.06. It's compounded monthly, and you're going to do that for 5 years. And we want to find out our accumulated amount. So this question itself, it actually doesn't use logs at all, because all we're going to do is just plug in everything that we know. Okay, so it's important that you know how to put this into your calculator. I'll trust that you can play around with it, but one common error is how people enter values within the brackets. You might want to double bracket this right here to show that that's a fraction, and then that may help out with the process. But make sure you don't just say, oh, that's the answer, I'll copy it down, but you take the time to be able to put it into your calculator, because the brackets do make a difference. So right here, I'm just going to enter this in, and if we do this, you should get an answer of let's see, whoops, $8,767.53. Okay, it doesn't say what to round to, but we'll round to the nearest cent. And understand that the question is saying find the interest. So that's our total accumulated amount. So let's actually subtract 6,500 from that. And if we do that, we'll be left with $2,267.53, and that would be the actual accumulated interest because you began with that 6,500 principal already. Okay, so let's look at another example. What initial investment is needed to become a millionaire in 25 years if you receive interest of 12% compounded quarterly? 12% is a very nice interest rate. Okay, so A equals P bracket 1 plus R over N to the NT. Okay, and so based off of that, we could say A, P, R, N, T. And they're saying, what's your initial investment? We're probably not going to know what our P is because we know we want to end up being a millionaire. And you're doing this at a rate of 12% compounded quarterly, 4 times a year, and you're going to do that for 25 years. Okay, you guys should take a guess right now and think about what amount of money you would need to do to be able to achieve this. And just remember, this isn't where you're contributing along the way. This is just saying, if I have this money, I put it into this investment and I let it sit there dormant for 25 years. Here's what would happen. So how much money do you think you guys would need to be able to do something like that? Okay, our rate is 12%, and that's going to be for 4 times 25 right there. Okay, so depending on how you want to approach this, what you may want to do is, with the previous question, we just put that all in our calculator in one go. With something like this, we want to isolate for P. I'm just going to clean things up slightly because we're going to have to do a tiny bit of algebra for it. So $1 million is going to equal P times, this is the same as saying like 1.03 and to the power of 100. And then I'm going to divide both sides by 1.03 to the power of 100. And then we'll have P isolated that way. So if you put that into your calculator, you should get an answer of $52,032.84. And that's an incredible fact. Think about this. If you had just over $50,000 and you could have this great investment, then imagine that becomes $1 million in 25 years just by letting it sit there. Okay. So let's look at this just a tiny bit more. And one thing we haven't addressed yet is, well, like, what's the difference between calculating annually or monthly or weekly or whatever it is? And so let's do a comparison and let's see how much of a difference this actually makes. One day, many of you are going to have a mortgage or something like that where the frequency of your payments can make a slight difference that could be worthwhile when dealing with very large sums of money. And this question here illustrates this a little bit. So basically, the concept of compound interest is that your interest makes interest. And so if you're using this for good, for investing, then that means that you can make more money more frequently. But if you're doing this to pay off something, pay off a mortgage, then that compound interest can also accumulate, and it can be something that could be very bad very quickly. So what would be the difference in example 3 here, where you have $1,000 and you want this to double, and it's working at an interest rate of 5.5%, and for the first case, it's compounded annually, once per year. Whereas in the second case, it's compounded monthly, every month. So the concept behind this is because you're compounding something more frequently, you're compounding something monthly, then it's going to be able to uh, earn more money more quickly, and the amount of time it would take to double will be less than what it would be to be annually. But how much time less is the question. Okay, so we have A equals P, 1 plus R over N to the NT. I'm not going to write out my different values on the side here. I'm just going to enter this in right away. Now, if we want an investment to double, we could write this in one of two ways. You could say 2,000 equals 1,000. We had $1,000 as our principal, and you want it to double, so your accumulated amount is going to be 2,000. But if you thought ahead and you said, well, can't I just say it's 2 equals 1 because I want my accumulated amount to be twice as much as my initial amount? Then absolutely, you could just say 2 and 1 rather than 2,000 and 1,000. The interest rate here is 5.5%. And it's compounded annually, which means your n value is 1. So it means we don't have to worry about doing r over n. It's just going to be an r value. And then it's raised to the power of nt, and our n is 1. And so our compounding period is what they want us to find. So we're just going to say that that's just a t. We're not sure exactly what it is. I'm just going to set up part B just so you can contrast that. So we're going to compare that to the idea of having $2,000 equaling $1,000 compounded at 5.5%, and that's happening monthly, so 12 times to the power of 12t. Okay, so think about this chapter. We're working with logs, and the big thing that we've said at the start of the chapter is that you use logs to be able to solve for exponents that are variables. And in the first two examples, we didn't have to use logs, but in this example right here, we have an exponent that's a variable. So this is a really rich example where we can now utilize logs to be able to algebraically solve for t. So let's think about what we would do. We divide both sides on this first example by dividing by 1,000, and all that does is just reduce everything to 2. And then if you have something that says 2 equals 1.055 to the power of t, we have to think about, well, what do we want to do here? If we keep it like that, then that's a pretty clean form of being an exponential form. And so you have two choices. If you want, you could log both sides, kick the t in front, and algebraically solve for t. I'm under more of the impression that if we're in exponential form, let's put it from exponential form into log form. And if we wrote this as a log, you would get log, your base is 1.055 of 2 is equal to t. So let's put that into our calculator. Remember, you should have your log base function on your graphing calculator. And if you do that and you put in these values, you would get something. I'm going to go to 2 decimal places. T is going to equal 12.95 years. Okay, so just under 13 years to be able to double your money. So that's part one of it. So then if I looked at this monthly part here, again, let's divide by 1,000 to begin with. And we get this value of, I could change that to a decimal. If you want to, you can, but it's probably a little bit messier. Now, right here, this one becomes a little bit more complicated depending on how you want to be able to do this. Your base obviously would look a little bit stranger. So if you want, you're welcome to put this into log form, and you could do something with that. But if you also want to try logging both sides, you could do that as well. So both are acceptable methods. I'm going to show you what happens if you log both sides. You could say log 2 equals log of this value here, which I know is kind of a repeating decimal eventually. What ends up happening is this 12t can kick in front using our soccer kick rule. And then if we wanted to isolate for t, you have 12 times t times log of that. So if they're all being multiplied by each other, you could divide by 12 log 1.1 plus 0.055 over 12. And then you do that over here, and the 12s cancel out, the rest of the log cancels out, and just maybe put this all in a double bracket there. So try putting that into your calculator and see what you get. If you chose to do it the first way by putting it into exponential form to log form, then that's also very, very good. And I probably recommend staying consistent. So you may want to try that instead. But here's another way to be able to do this. Okay, and if you do this, you should get something where t is going to equal 12.63 years. And so think about what this is saying. This is saying that I could save upwards of a third of a year or so in terms of being able to reach my goal for my investment by compounding something more frequently, by compounding it monthly rather than compounding something annually. So it's a very interesting concept, but that's basically what it's telling us. So it's not life-changing. It could be if you're working with very large sums of money, but basically that's how it works. If I'm not sure if in econ, if you guys study this or not, but there's a really cool concept called the rule of 72. And if you are interested in this type of stuff, you should definitely Google Rule of 72 and look it up. And what it talks about is the time it takes for money to double, where you could do something quickly in your head. And it actually doesn't have to be money. It could be a population size or something like that. And so what the rule says is money approximately doubles when you take 72 and you divide it by whatever the in this case whatever the interest rate would be. So if we took 72 and you divided it by 5.5, you get 13.1, and that's just saying it would take about 13.1 years to be able to double, and that 13.1 is pretty close to our annual interest of 13 years. So it's kind of a cool way to be able to approximate things very quickly in your head. Obviously dividing by 5.5 isn't super clear to be able to do the mental math for it, but imagine if you're talking about not 5.5% interest, but a clean number that's divisible by 72, like the number 8 or 9 or 6 or 12 or something like that, then you could find out those doubling times really quickly. If they said something like this, if you compounded at 6%, for instance, and you did 72 divided by 6, then that would say it would take approximately 12 years to be able to double. So kind of an interesting concept. So just to be clear, if you compound daily, that would be 365. If you compound semi-annually, that would be 2. If you compound weekly, that would be 52. This is my fun fact. If you're never sure how many weeks are in a year, the number of weeks in a year is the same as the number of cards in a deck. So in the same way that there's 52 weeks in a year, there's 52 cards in a deck. And in the same way that there's 4 seasons, there's 4 suits. And there's actually 13 weeks per suit or per season, in the same way that there's 13 cards per suit. So okay, now let's go through a really big concept here. It's too bad that pre-calculus doesn't talk more about the value of E. And when you get into calculus, you're going to see that you end up using the value of E all the time. And it's basically a number that has so much richness to, and I hope that when they rewrite the curriculum next, that we get a chance to be able to talk about this a little bit more. So here's what's going to happen. I want to talk about for maybe 5 minutes or so. The value of E is a number that's it's actually on your calculator, and we'll show that in a second on how to be able to find it. But I would say I would rank it as probably the second most famous irrational number after pi, and it's named after Euler, who his last name is spelt with an E-E-U-L-E-R, and basically here's how it works. If we're talking about this idea of compound interest, and we said by compounding something monthly over annually that you can basically earn more money more quickly. Well, what would happen if we didn't compound something monthly, but what if we compounded something by the week? Or what if we compounded something by the day? Or what if we compounded something by the hour? Or what if we compounded money by the minute? Or what if we compounded interest continuously? And if you do that, what would happen? And it's a very interesting investigation. In fact, it would be the type of thing that you could say, well, if I do that, then could I make an infinite amount of money? Like, what happens here? And so you could take this concept where you could say something like this. Imagine you had $1 and you had this great option of being able to make 100%. Okay, and you can make 100% compounded annually. Okay, so if you had something like that, and you took $1 and you compounded it at 100% compounded annually, and you did that for 1 year, then you would end up with $2. But now say you did something like that and you compounded it semi-annually. Well, you should probably make a little bit more money. So we're going to say that this is going to be using our formula 1 plus r over n, where n is the number of compounding times. So now that's a 2. And we put 1 on top because 100% is 1.0 as a decimal. And if you put that into your calculator, you end up with $2.25. So obviously compounding semi-annually is better than compounding annually if you're making money here. Well, what would happen if you compounded something monthly? Well, if you did that, let's see what you would get. You would get 1 plus 1/12. You get $2.61. Okay, you're definitely getting more, but maybe it's not quite as much as what you thought. What if we compound something weekly? Okay, so if you do something like that, surely taking something to the power of 52 is going to change things quite a bit. So if you do 1 plus 1 over 52 to the power of 52, we get 2.69. Okay, now our value going from monthly to weekly didn't change that much. I got an extra 8 cents. And so even though I took something from the power of 12 to the power of 52, it barely affected it. And so think about what would happen now if you put in a massive value. So if you're going to compound continuously, you would basically be saying you have something like this. You're going to say, I have a massive number that I'm compounding all the time, and I'm taking that to that power of that same massive number. And what happens is you end up with the term or the value of E. So take your graphing calculators right now, and if you take your graphing calculators and you press second divide, then you'll find this value of E. And you'll see that E is approximately the number 2.71828 blah blah blah. It might even look like it's rational because the 1828 repeats, but I assure you it's not rational, and it would be an irrational number. And what that would say is if you compounded continuously, you would make $2.72. So that's how that concept works. Very, very interesting stuff. Again, I would look up things. I would maybe take a look at Euler and see what you could find there. Okay, so if you have this, you could put this all together, and basically you could create your compound interest, your continuous compound interest formula. And here we have, when you take your principal and you compound continuously with the value of e, then you still take that to that same power of how many compounding periods do I have, what's my rate, and for how long. So here's our rate as a decimal, and then here's my time, and then here's my accumulated amount. Whoops. Okay, so right here we have the note. E is approximately 2.71828 dot dot dot. And let's see what we could do with this. So when you pair something that has the value of e, we could take the log of it, and that's actually totally fine. And there's nothing wrong with taking the log of it. But besides taking the log of it, you could actually also do something called taking the ln of it. And the ln is a natural log, kind of a different term that you're saying, like, I can't believe there's a second type of log here. So if you look on your calculator, on the left side below your log is your ln, and you should take a look at that and you can see what's there. And basically what ends up happening is this. If basically when we talk about logs, they're denoted in base 10. And so if you have something like log, let's see, log base 10 of 10, that equals 1 by definition. But when you talk about a ln, your ln, it has a denoted base of e. And so it makes it a lot easier when you deal with this value of e to be able to use lns instead of logs, because it can make things very clean. So for instance, if you took the ln of e, you just get the number 1. So you should make sure that you see that right away. I would say on an assessment, you're barely looking at this concept of E, just because it's not covered much by content, but I think it's something that you want to make sure you understand if you plan on taking calculus, because it's a really interesting idea. So ln of E is equal to 1. This is a really strange story, but I remember actually talking to a friend a few years ago, and I was texting with them, and I remember saying, "Oh yeah, that's a good one." And so on my iPhone, I was like, "Oh yeah, that's a good one," and I type out "good one," and for whatever reason, I typed out "good LNE." And I just thought it was the funniest thing that I've ever done, because it said good ln e, and if you think about what ln e is, it's actually saying good 1. So I actually typed out what I intended to type out. Yeah, okay. Amazing math memes there. Okay, here we go. Yes. So when I said that, it was pretty cool, because I never got auto-corrected. I guess maybe like the iPhone is smart enough where they understand that I intended to say good one as well. But anyways, I'll probably stop there, because I think I just lost a couple cool points. Okay, so let's look at these next two examples right here. So this is just having the value of e, and they're saying, well, what would happen if you were able to compound something with that? So solve these questions. I would say, again, let's actually start by, let's ln both sides. So ln 45 equals ln e to the power of 0.075x. Okay, and let's kick that in front, and I'm going to rewrite that. Ln 45 equals 0.075x of ln e. So again, if you logged both sides, you'll actually get the exact same answer. But the thing that's so nice about this is when you have this ln e right here, you can just cross that off because you know it equals the number 1. And then you can divide both sides by 0.075, divide by 0.075. And then you could say, okay, let's find this out. Ln 45 divided by 0.075. And we get something that would be 50.755. Okay, and then for our next example here, we have another value here that remember that doesn't have the exponent of 0.045x, so we should divide both sides by 5, and then you could say something like 300 is equal to e to the power of 0.045x. Again, you could try and put it in ln form right away if it's an exponential form, or you could ln both sides. Either or is good. Okay, and then you can kick this in front. Ln 300 equals 0.045x of ln e, and very similar types of calculations. So you could just say ln 300 divided by 0.045, and if you do something like that, whoops, you get 126.751. Okay, let's do one more example. Okay, so it says estimate the time required for $5,000 to grow to $30,000 if it's invested at 10% compounded continuously. Okay, so once you see this term compounded continuously, then you're using, your continuous compound interest formula. You'd be given something like that for the question or on any sort of assessment, and they're saying $30,000 is your accumulated amount, and that happened when you began with $5,000, and it was e to the power of RT, and we want to find out the time. Okay, so given something like that, I would pause the video right now and see if you could isolate for t. Okay, so if you have something like this, let's ln both sides. Ln 6 equals ln e to the 0.10t. Ln 6 equals 0.10t of ln e. And if we put that into our calculator, we get 17 point, it doesn't say how much to round it to. Okay, we'll say 17.9 years. Okay. So hopefully something like that seems pretty reasonable, and that's how compound interest works, and that's how continuous compound interest works. So this is part 1 of a 3-part series for log applications. So what I would do is I would pause the video right now. I'm not going to assign any homework yet because we're going to do a part 2 of it. After you've watched the second part of the video, then I think there's a couple questions to be able to work on, but it's more building up all these different tools for different types of applications. Thanks.